Any questions about anything so far? Everybody can hear me and see my screen. Just one person can say something. Ellen? Yes. Anna, can you see?
Yes.
Okay, very good.
Here.
Excellent. So let's just start it. We'll start by going over the homework. Oh yeah, by the way, just if you could log into Gradoscope right now and submit it. Yes, let's take while it's loading. On this end, yes, please go to Gradoscope and submit your homework. And as you're doing it, we're going to start going over it, right? So the first one assignment was that given two Boolean functions, f1 and f2, we want to show that the sum of those functions, function e, will contain the sum of the minterms of f1 and f2. Right? So let's just come up with an arbitrary functions, right? This is not going to be quite a rigorous proof, but something along the lines we'll be able to show a couple of rules, right? So we'll have these two functions as arbitrary functions within the set B that are going to be expressed in the canonical standard form, right? Which is going to be sum of products of all three variables, or we also call them minterms, right? Okay. Here's our arbitrary example, and we'll come up with a solution to it, though it's not a formal proof. It's a hint, or even more than a hint, right? We'll be able to come up with some rules. So here we have two arbitrary functions, but they're both in canonical standard form. So they're made up as sum of products. Each one of them is a minterm, right? It's a product of all three literals. Okay. So here we have function e, which is the sum of our function. And it's going to be essentially just the sum of all midterms, right? So just or, the first four midterms are going to be from f1 and the last three midterms from f2, and total of 7 midterms. But just by the way we designed the example, there may be an overlap, right? Some of the midterms may be the same, like the very first one, xyz, xyz, right? So we have it twice. So let's look for the ones that we see twice. So that's one of them. And here's the other one, right? All of the other midterms happen only once. Complement of x, y, complement of z, complement of x, complement of y, complement of z, and x complement of y, z, right? Those are unique. Now, the ones that are not unique, we're going to, sort of collapse them, right? We don't want to mention something double, right? Because of the idempotency axiom, right? xyz or xyz is xyz, right? Same thing for complement of x, yz. So now, instead of having 7 midterms, we only have 5. Okay. And that's sort of like the result here. And to generalize this, E function will contain all minterms in F, ORed, or added, or plus, to all the minterms in F2, right? So that is what we did. And the only simplification that can happen with minterms, right? You could simplify this perhaps a lot, but then you will depart from the canonical form. You will not have minterms anymore. And that can be okay, but the only simplification that can happen with minterms that are common to F1 and F2, which is it will appear, will make them appear once, right? So that's the simplification that we did there. Any questions so far? Okay. Now, B is show that Boolean function g, a different function, is a product of f1 and f2, will contain only the minterms that are common to f1 and f2. Again, we're going to consider this example in the same way. We'll use the same f1 and f2. And we're going to multiply them. Right? So here we have them. Instead of adding the midterms, we're multiplying all the midterms from F1 by all the midterms of F2. And what will happen here? Any ideas?
It should simplify down to just the common terms.
Yeah, it will simplify down to just counters. For example, we have to multiply all by all, right? So for example, the very first thing we'll multiply is the xyz multiplied by xyz because of the, again, idempotency axiom, right? xyz multiplied by xyz is still xyz, right? But as Patrick correctly suggested, some of the other ones will reduce, right? So if we keep multiplying, and we'll multiply xyz by, the next one here, complement of xyz, what will happen? Right, just those two. Anybody else? Right. What will happen when we multiply xyz by complement of xyz?
It will be
0.
Yeah, it will be 0.
Why?
Because x times x complement is 0, and
That's right.
0, 0.
That's right. So what will happen is that any of the minterms that are not in both, right, in the multiplication, they will encounter a minterm from the other one that has at least one complement term, right? So variable, right? So for example, here with xyz multiplied by complement of xyz, right? So x multiplied by complement of x is 0, and everything else, all of the yz's there, multiplied by 0, they go away, right? So that is what will happen to all of them, except for the ones that are common, right? And as it happens, there are two minterms that were common to both, and those multiplied by themselves will remain. So any questions about that? So if we express it as a general rule, right, we'll say that G will contain only the minterms that are common to F1 and F2, because two-part, right? First, the product of identical minterms gives you the same minterm as a result, right? xyz by xyz is xyz. Okay. And then if two minterms are different, then they will necessarily differ in at least one variable, and that in this case it can only be the variable or its complement, which will appear in its true value in one term, meaning let's say x, and its complement value in another term, x complement, right? And they will nullify each other. In the product of such different minterms, after possibility, commuting variables. Commuting meaning like here I have everything alphabetical, but in the real world it may not be, but it doesn't matter in what order x, y, and z happen. And so commutative. We must have the product somewhere within each multiplication where it's true variable by its complement, which by 5 is 0. Thus we have the product of two different minterms is always 0. Again, the product of two different minterms is only 0. Only a product of two identical minterms is 1, right? It doesn't matter how different the different ones are. They could have one variable off, two variable off, all three variables off, right? 0. And so those are, well, that's the result, and these are the two rules. Okay. If there were no questions about that previous assignment, let's do this one. Right? We're going to build a truth table out of this function. Right? We know how to easily and quickly build truth tables out of a function expressed in minterms, right? It's just like each minterm becomes like is where the function is 1, right? And you just copy, 1 for true literal, and 0 for complement of literal, right? So we can try to convert this into the min-term version. It's not difficult, right? So, but right now it's a simplified standard form, still standard, right? Sum of products, but not canonical, no min-terms. Again, the sort of like the base of the truth table is always the same for the same number of variables, right? We do it in the sort of like numerical value increase, starting from 0, in this case ending with 15. If we had 4 variables, it would end in 31. If we had 2 variables, it would end with 7, right? And now let's give the entries in the truth table corresponding to the 2 literal terms, right? Each term here is made up, these are not min terms, but as they are, each one of them are made up of 2 literals. So the first 2 are made up of xy, the last one is made up of yz. Right, so now we'll try to, as quickly as possible, as easily as possible, come up with the function value for each of those products, right? Now, of course, we can expand every 2 literal term to min terms to identify the triplets in the truth table, right? So, question to you guys and girls: how can we easily expand each of these terms into min terms? And the follow-up question is that how many min terms will each one of these terms produce?
Can we add, the missing, so to the first one, x, y, add a z, and also duplicate it and add a z prime, and then the next.
Well, you don't truly need to duplicate it, right? But you're right, yeah. So what we're going to look at, like for example, in the first one, we have x and y, but we're missing z. So correctly. What is your name again?
Guy.
Guy. Okay, so as Guy says, we need to add z there. And what is the way to add a z here?
Add a z plus z prime.
That's right. We're going to multiply it by 1, which is totally legit, and then we will express that 1 in parentheses as z plus z prime, right? So that will maintain, perfect equivalence. And now we will multiply it out, and we'll get xyz plus xyz prime. So then my follow-up question, if somebody else can answer, it looks like this term became how many min terms?
2.
2. Yeah, and we're going to do that for the other 2 as well. And we should get a total of 6 min terms. Right? So that was the first pair. And before we do that, notice that because the z's are 0, 1, 0, 1, 0, 1, these 2 min terms will produce 2 1s, and those 2 1s will go next to each other. Everyone sees that? Right? So what we're literally doing is that we have 2 rows, 2 combinations, and in both of them, x and y are 1, right? So these are true values, they're not complemented. So x and y are 1. And z doesn't matter in a sense, right? And that's why it's not there to begin with. So z can be either 0 or 1, and the result is going to be 1. Right? Now, if we could have done that directly, but we didn't. We unfolded it into min terms. But now that we know this, we could do it directly faster, right? So what we know is that if we have a term, a product, and one of the literals is not there, one of the variables rather, not literals, one of the variables is not there, we know that that variable doesn't matter in the sense that its value doesn't matter, could be 0 or 1, right? so that we get these two combinations that share the value of x and y and differ in the value of z, and they're both 1. Any questions about that? Okay, so now we can do this again. Oh yeah, and of course, these are products, right? So 1 multiplied by 1 is 1, as this x multiplied by z is 1. Okay, so the second pair is this, or the second term, the second product is x multiplied by complement of y, right? And that will be, again, 2 rows. So x is the true value, 1, 1, and y is the complement, so 0, 0. All right, so it looks like these 2 rows are also going to be 1 independently, or no matter what z is, right? So either 0 or 1, so this is still 1. Now the last one, we have y, complement of y, and z, right? So x is not there. So who can tell me which 2 rows we'll be looking at? Complement of y and z. And you can name the rows by their number, like 0, 1, 2, 3, 4, 5, 6, 7. So for the last product, complement of y, z, which rows are we going to look at?
So the first and second.
So this is the first, and this is the second. Is that what you meant?
0th and first, sorry.
0 and 1. All right, so what we have here with 0 and 1, we have complement of y, yep, 0, 0. And then we have z. So in 1, z is 1, but here the 0 doesn't look right, right? So in order for z to be 0, it would have to be z complement. So I agree with you on row 1, but not on row 0, maybe, right? Or actually, what am I saying? Yeah, right? So y is complemented, right? Y is 0, and z is 1, right? So 1 looks good, but not row 0. So what would be the second row that would work?
There isn't any, that's the only row.
Row 4 or 5? Wait.
Yeah, 101.
Which row?
The one that says 101.
101, right?
But that's
So,
already 1. We already have that.
well, that's fine. That's fine. So let's just double check. So y complement, y should be 0, and z should be 1. So yeah, looks like that. Looks like 1 and 5. And there they are, right? So they don't need to be unique, but they can overlap. That's fine, right? Even though we express this expression that way, it doesn't mean that we will have an even number of ones, right? So it sounds like we have a question. Go ahead with your question. But yes, the students who suggested 5 are absolutely correct. So it's 1 and 5. Question.
Hi, I just wanted to ask if you could give a couple more minutes to submit the homework because I overslept and I didn't get to submit it.
Yes. So please be on time. But yes, I'm going to. I don't want to exit the presentation now, but just be ready. And then at some point in the lecture, I will say that, oh, I'm going to unlock it now, and you'll be able to submit. Okay.
Okay, thanks so much.
Good. So how about any questions about what we did here? Right. And if you don't value your time, right, you can just unfold it into, expand it into the midterms and do it that way. But I think it's good to do it this way. Obviously, it's faster, and it also helps you be comfortable with what the whole project of, or most of the semester, is to move into further and further abstraction, right? Abstraction. So we start with these Boolean functions that can be easily translated into English language with and or, maybe but and nor, whatever, and we're moving to just like ones and zeros arranged in tables, and in a minute you'll see geometrical shapes, like even three-dimensional ones. Okay, so this is useful. Okay, so the remaining triplets all correspond to the zeros, right? So the remaining three triplets, three combinations, the value of f is going to be 0. Okay, so if there are no questions about homework, then now we're starting a new topic, traditional minimization methods, right? And there are two methods. One is called Karnoff map, or K-map. And then the other one is the tabulation method. We'll also touch on to that, but right now let's concentrate on the Karnoff maps. So Karnoff map, you can think of it, it's similar to a Venn diagram, right? So as I said, it's helpful to conceptualize sometimes these Boolean algebra expressions in terms of set theory, right? So Karnoff maps, maybe along those lines, you can think of them of like Venn diagrams. Now we're going to visualize the functions and its simplifications. Another way to initialize it. So we'll start with a simple function that only has two inputs, two variables, x and y. And we're going to view them as sets that are non-identical, right? Because if they were identical sets, then you would really have only one input, only one variable, right? If x were equal to y, then you wouldn't need y, you would just have x, right? But that isn't clear, just ask me. So that means that the x and y are going to be non-identical sets. So there will be areas where they don't overlap. There may be areas where they overlap or not, right? But they're different sets. And here we're going to draw kind of visual representation of them. So this was what the simplest Karnoff map looks like. So we have, if you look at the square, the part on the left of this red line is the set of x. And the part on the right of this red line, these two cells, are the rest of the set that is not x, right? Together they will make up a whole set. Okay. And then if we look at it in the other dimension, we have this green line that separates the y from not y, from complement of y, right? So would you say that if we add y and not y, so we say y area plus complement of y area, so think of that as a set, and then we have the x area and or complement of x area, right? So these two large areas, would you say that they completely overlap or not? Not just x and y, but x or complement of x is one, and the other one is y or complement of y. Would you say that they cover the same area? And if yes, what is that area?
I would think they don't, since they have different, since they're different, right?
Well, x is different from y, that is true, but it's not just x, it's x plus or complement of x, and then y plus or complement of y. So any other ideas?
If they're all ORed, then they cover the entire area.
That's right, because y or complement of y is the whole thing, the whole entire possible set. And x or complement of x is also entire possible set. And yes, it's just one set. They live within one set. They're both, within B, whatever you want to call it, right? So yeah, if you, or them with their complement, then yes, they will include the entire thing and completely overlap. And that is this blue rectangle. The blue rectangle is the entire set, and both of them bisected. They divide it into y, and the rest is complement of y, x, and the rest is complement of x. But if you or both of the green ones and the red ones, they will overlap into this entire set, which is the purple rectangle. Does that make sense to everyone? And what it allows us to see is where individual intersections are, right? So this little corner is where x and y intersect, so their common area. And this little corner is where x and complement of y intersect. And this little corner is where y and complement of x intersect. And the last one is where complement of y and complement of x intersect. Okay, so there we have it. That's our map of the entire set of the universe. Okay, now of course these are not sets. Okay, well, this shows what I just said, right? The intersections, or you can think of them as products. Okay, so just a picture of what I just said. So each possible minterm has a position on the K-map, right? Have a region for each possible intersection. If a function has only two variables, that means that it will have, in this case, two minterms. Each minterm will be the product of the two variables, and Karnaugh maps will have a little rectangle for each of the minterms that represent a function. Right? So it's really just minterms, but instead of them being in one line with plus, 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 we're arranging them at what looks like a little table. Okay. That was, of course, the simplest one with two variables, but our previous examples had three variables. So, perhaps ideally we would do it in 3 dimensions with a cube instead of a square. But we don't have that luxury, we have just paper. So we're going to put z's sort of at the bottom here, right? And but sort of have them also between z and complement of z cover the whole set. Right? I'm going to make the rectangle a little bigger, a little longer, make it more eccentric. Eccentric means longer than wider. So for example, an ellipse is a stretched circle, right? A circle made eccentric, and a rectangle is a stretched square. And then you can compare it to rectangles. The one that is longer with the same width is more eccentric. Anyway, so that's what we did here, so that we have more room. And we want to create all possible intersections, right? So with 3 variables, we would have here 8 possible minterms. Not actual minterm, but 8 possible ones. It may, in the end, it may only have 1 or 2, but it will have at most 8, right? So we need to have all those intersections so that, let's say, the area of 2 x's should not completely coincide with the area of 2 y's or the area of 2 z's. So if x is the left half of this whole thing and complement of x is the right half, and if y is the top half and complement of y is the bottom half, what we're going to do with z is say that z is the middle half, as it were, right? That's z. And complement of z is going to be everything else, which means that it'll have to be on the sides. Okay, so I'm going to pause here for 1 second, and I want everybody to see what I did there. Right, so by doing that, I ensure that I will have all possible intersections of x, y, and z. We will, in a second, see that the arrangement of these things matter, right? And specifically, we want to arrange them in such a way that all x's, all y's, and all z's are contiguous, meaning sort of touching each other in a way that, or rather, x and x complement of x, y and complement of y, etc. Right? So we have x here, and then we have complement of x here, right? Then we have y here, and then complement of y here, right? They're contiguous. And we have z here, contiguous. But complement of z is split, right? But it shouldn't be. So the only way then we can, connect it is to take this rectangle, eccentric rectangle, as a strip of paper, bend it around, and glue it in the back, right? So that it will become a cylinder. And that way, the z prime, complement of z, the four squares that are complement of z, will become contiguous. Can everybody imagine that? In other words, whatever we're doing with these K-maps, when we reach this edge, the right edge or the left edge, we imagine that they connect in the back. Just these two for now. Any questions about that? Okay. So if we do imagine that, then we have all of our possible minterms, right? We have, this is the x area, this is the complement of x area, right? So nice and tight to each other. Then we have the y area, again, all together, and then the complement of y area all together. Then we have the z area all together. And then lastly, we'll have complement of z area. It looks like it's split in half, but really it's connected in the back around. Okay, cool. And these are the 8 possible minterms here. Now, an example of an actual function that is not all. So let me just pause for a second. I just told you that we could have a function, right, with up to 8 possible minterms. So if I had a function f that in fact had 8 possible minterms, what can you tell me about that function immediately without like thinking too long? So this particular function f has 5 minterms, which is fine, less than 8. So what if we had a function that had actually 8 minterms, which we can, it's possible. What can you immediately tell me about that function?
It's
gonna be
1.
5 ones and 3 zeros.
No. It's, yeah. So yes, this function that you see on the picture is 5 ones and 3 zeros. But the other student answered my question, which was, what can you say about a function that has 8 minterms? Could you repeat, please, what you said?
At least one of them is 1, so the function would be 1.
Yes, that's right. Which means that this function will always be 1. So you really don't need any minterms. You would just say f equals 1. It means that with any input that function, it would be a tautological function. It would be always true. Could we have a function that had no minterms, 0 minterms?
Wouldn't that just be 0?
Yeah, it would be a null function, f equals 0, again, tautological or whatever, always false, right? But these are weird extreme cases. But as the other student said, in this particular function, we have 5 minterms that, yeah, it means that it'll have 5 ones and 3 zeros. So let's see what that looks like. So we're going to have the same K-map, just a little smaller. And yeah, there's X, Y, and Z, like our, the axes. And then we're going to put a 1 in the place of each mean term as the value of f, right? So the first mean term is x, y complement of z. So x intersects with y, and then intersects with complement of z. So where will my first one go?
Bottom left.
Which one? One more time.
Is the bottom left or?
Bottom left. Any other ideas?
Wouldn't it be top left?
That's right, top left, right? Because bottom left would be x and complement of z, but it would also be complement of y, right? What we want is x, this big square, and intersecting with y. It's this like rectangle. And then we want to intersect it, that little thing, with z prime, complement of z. So this would be z, true value, and this is the complement, correct? So we put the first one there, and then we'll do that with the remaining 4 min terms. So x, complement of y, complement of z is below, as one of the other ideas proposed before. Then we have complement of x, y, z, right? That would be complement of z. Go there. And then the next one will go complement of x, it's this right half, then y, the top half of that, and then complement of z, so that'll go here. And the last one, complement of x, again, complement of y, and complement of z. So this is the K-map for a particular function, for this function f. The rest of those are zeros, but you can just leave them blank. So now we're going to group them, right? And we can group them if they, touch each other. And when we do that, we can express that shape, that little, oval or whatever you want to call it, or ellipse. We can express it as a simplified term, right? As a simplified product. So why, can somebody explain to me, why can I express this whole ellipse that covers 2 adjacent cells? I'm expressing it here. It's made up of 2 min terms. Each one is a product of 3 variables. And here I just drew a shape around it and say, oh, I'll call it x multiplied by complement of z.
Because it doesn't really matter what y is, because we're saying it's 1, whether it's y or y complement, which is just the whole end of y.
That's exactly right. It doesn't matter what y is, because y could be either y or complement of y, right? So this is what we did just a couple of slides ago, but in reverse, right? Instead of taking a product of 2 and going to 2 min terms, we're taking 2 min terms and going back to the product of 2 variables, right? Any questions about this? And I'm going to try to do it a few more times with this K-map. Okay. So by putting together 2 adjacent squares, we form a size 2 implicant. Yeah, basically, this single implicant implies everything inside it, right? So this single thing, implies that x, y complement of z is 1, and x complement of y complement of z is 1, okay? Now, notice that these adjacent squares will have become sort of like doubles, right? So you can connect 1 and 1 and you get 2. Okay, let's see what else we can do. We can connect these 2 ones, right? This is both y and complement of y, right? So it's also going to be a term with x and z. So now it's a complement of x and complement of z, right? So that's also an implicant of size 2, right? It's a single thing here, complement of x multiplied by complement of z, that applies these two min terms. And then we can take those two size 2 implicants, and because this thing is glued in the back into a cylinder, right? Both of these things are touching each other in the back, right? So we can connect them together and create a larger implicant that will, engulf both of them, right? So what will happen, or how will this big implicant be expressed if it encompasses x complement of z and complement of x complement of z? So this will be also a term, right? Not a prime term. I mean, not a min term, sorry. What term imply, right? It will be a big implicant. So what will be the term that will imply all of these four ones? Right? I'm putting together now x complement of z, complement of x, complement of z. Come on, somebody.
Is it just Z
Right? By putting two single ones together. That's right. Exactly right. That's Stephanie?
Yeah. Yeah.
Okay. Yeah, just I think I'm familiar with some of the voices, but if you could just like say correct. So Stephanie is exactly right. Yeah. This big implicant, the red one that encompasses both of the blue ones, is going to be simply complement of z, right? Because it doesn't matter what the y is, could be either y or complement of y, and it doesn't matter what x is, could be either x or complement of x is, right? So in this particular function, it's being simplified a lot, where we have one of the terms that is simply complement of z. Right, and it's written here twice, but it's really one thing, right? Because it's connected in the back. So again, by putting together adjacent size k implicants, we form an implicant of size 2k. Yeah. So, and that is the general rule. So if we put together two single ones, we get one of size 2, which is double of 1. And then when we put together two of the double ones, so individually it's size 2, but together they become size 2 multiplied by 2, or size 4. And we will give these implicants names, so this giant one, we'll call it A. And A is equal to complement of Z, right? And that's going to be one of the, well, very much reduced terms to express this function.
So, I'm sorry, can you just repeat what implicant means?
So we call them implicants because they imply smaller things inside themselves, right? So we have this A thing, and it implies that there are 4 ones in these 4 rectangles, right?
Oh, okay, yes, thank you.
In fact, and like in English, implies sounds like hard, right? If we say that there is an A.
Sorry, could you repeat that? Your mic cut up when you said in English.
Yeah, in English, when you say to imply, you're sort of maybe mean it or maybe not, right? It sounds a little bit soft. But in logic, implication is absolutely hard, right? So if we say that one of the implicants is A, and that is its shape, then we're absolutely asserting that every square inside A is 1. Okay? Like, no question about it. Okay? So A by itself implies, or definitely says, that we have those 4 ones inside it. Alas, there is another one here, the 5th one, that is not part of A. Right? So A does not encompass it. And that particular one could have been expressed by, let's see, x prime, y, z, right? So we can just have it as a separate term. So then this function would be expressed as z prime plus x y complement, no, sorry, complement of x, y, z. But we're actually going to try to put it together with something else to make some, rather than keeping it as its own thing, we'll try to just connect it and make it into another implicant. And the only one that it's touching here is the one to its left. So I'm going to put a black ellipse around those two. And again, I connected two. So as you see, we can duplicate. We can use the same one inside multiple implicants. That's allowed. So this particular one in the top right corner is part of both A and whatever I'm going to call this one in a second. But this one connects two squares of size 1 into an implicant of size 2, right? So whenever you make this connection, this union, the size sort of doubles the size of the unit. And I'm going to call this black implicant B, right? I cannot join, or I cannot connect it to a larger implicant, right? Because there is nothing that is adjacent to it but doesn't intersect it, right? So it remains its own. So now I have A and B. So this way we can only form implicants of size 2 to the power of k for some k, right? So that means that implicants cannot contain 3 elements or 5 elements or even 6 elements, right? Implicants can only have, well, 2, right? Like blue and black, or 4, like red, or possibly in the future, in larger maps, we can have implicants of size 8 or of size 16 or 32, etc. Do the rules make sense? Okay. So this function now, f, will be expressed simply as a plus b, where a equals to z prime and b equals to x prime y. Right? And then if we express it that way, it's going to be fully equivalent, a plus b, to what we started with. Questions? Okay, project.
Wait, how is it a plus b? I thought they were all. I thought it was times.
Well, these are so our standard terms, right, or whatever standard representation is sum of products, right? So we start with the sum of products. These are min terms, right? The canonical sum of products, and we're simplifying it into shorter sums of simpler products.
Right. Okay.
Right? And, so I don't have to use a and b. I can just say that f, this function, will equal to z prime plus x prime y.
Okay. Gotcha.
Okay, good. Good question. Okay, now let's talk more about the implicants. The larger the size of an implicant, the fewer literals it contains, right? So if we had just a single thing, it would have 3 literals, just any of these ones. But once we put them together like B, right, it's a little larger, and now it will contain only 2 literals, right? And our biggest implicant, the red one, A, contains 4 ones, right? It's the biggest one, and it only has 1 literal, Z, right? Again, the larger the size of an implicant, the fewer literals it will contain. A prime implicant is maximal relative to set inclusion. That is, it is an implicant that is not included in another implicant, right? So we'll see an example of that in a second. So a prime implicant is the maximum, is the largest implicant that is not included in another implicant. Okay. To obtain a minimum form, we want to form prime implicants only. And when I say included, I mean fully included, right? So for example, the 2 blue ones, the x z prime and x prime z prime, they're fully included in the red implicant, right? And so those are not prime implicants. But A itself and B are prime implicants because, yes, they intersect a little bit, but they don't overlap completely. So to obtain a minimal form, we want to form prime implicants only, right? So we're going to, once the 2 blue ones were subsumed by the big red one, A, you know, we forget about them. You know, they're not going to be part of the formula, right? We want prime implicants only. Questions about that? Here, in this example, A and B are the only prime implicants, and you know, all of them. So let's make a note that for the purpose of being adjacent, these 2 sets of edges are considered identical. What are these 2 sets of edges? Right. Identical. Identical. And the third couple. Sorry. Basically, it's not just a cylinder, right? It doesn't just connect in the back. It also connects top and bottom. So it's really what it is. It's a donut or a torus, right? So that's the fancy name for it in geometry. So I have to bring that back. Actually, you know what? What will be faster if I show you a slide from the publisher slides. Oops. Plug this in. Okay. Yeah, this picture. Right. So you don't need to look at the specifics, but let's look at the shapes here. We'll look at the specifics of the slide a little later today, but right now, so if we look at this K-map in the middle, it's a K-map for 3 variables, right? X, Y, Z. That's very much like what we looked at just a minute ago, right? And then, as I told you, the 2 edges within the 2 vertical lines within the Z prime, right? They connect in the back. So we glue it together and it becomes a cylinder. But now I'm telling you that the top and the bottom also connect. So then it becomes this shape, looks like a, a lifesaver, a donut, a bagel, or a torus, right? So it's connected top and bottom in left and right. So I want everybody to imagine it. right? It's the same cells, right? Here it's 8 cells, right? And they're counted, you know, they have their numbers, you know, and the numbers are weirdly arranged, but 0, 1, 2, 3, 4, 5, 6, 7. And here, you know, it's the same numbers, right? And they're next to each other in the same way. So 0 is next to 1, boom, boom, right? And 0 is also next to 2, yep. And it's also next to 4. No? Where is 4? I think 4 is in the back. Yeah, 4 has to be behind it somewhere. It's strange. I thought they would have put all of them. 0, 1, 2, 3. Okay, they don't have the ones on the back of the torus. And then 0, so 0 is going to be next to 4, next to 1, next to 2, and I think that's it. Anyway, torus. Okay, any questions about this? No. Okay, good. So let's get back to our lecture. Again, so this is the picture that we were seeing, that so these two edges are connected in the back, but also the bottom and the top edge are also connected. Okay. Give it a second. It's starting up. Again, any questions that you're coming up with, just ask me now. We have a moment of silence. Okay. So from the previous page, this is our K-map with our 2' implicants A and B. Okay, right? So same thing from the previous slide. Now the goal here generally, right, with some kind of any possible function, is to cover all the ones with the least number of prime implicants, meaning largest possible implicants, right? So here we had to we're able to come up with the least number of implicants to cover all the ones 2, right? And we used the largest possible ones. We used, you know, the big giant one A and the smaller one B. So you know, and you often can do it in different ways, right? But it will not be, you know, you will not necessarily meet these 2 conditions, but it will still be equivalent, right? You could just left the 5 ones and had 5 min terms, right? And it just would be what we started with. But could you have the same number of implicants too, where let's say one of them is not prime, that would still cover the whole thing? So A, right, is, you still have to use A. Could you use something other than B to cover all the ones and still get a total number of implicants that's 2? You will not meet the second requirement. But you know, you would have an equivalent function that would cover all of the ones. You would have 2 implicants, one of them would not be prime. So you would still have the A, so you would say...
Could you use X prime Y Z?
Yeah, you could just have a trivial implicant that is just a single one. Yeah, and it will still be equivalent. But it would not be a prime implicant because it would not be largest possible, right? So the largest possible that would cover that one is this B, right? And as a general rule, if we just do it always, we stay within these rules, right? The least number of prime implicants, meaning the largest ones, largest implicants possible, right? Least number of the largest implicants possible. Okay. Or in other words, right, saying that this function is complement of z plus x complement y z, right? We have still two products, but the second product has three literals, right? But when I do the largest possible implicants, then the product is the shortest possible, only two literals, right? And what I ended here in the end is that one product that has a single literal and the second product that has only two literals, right? So by following this rule, list number of largest possible implicants will produce the simplest possible expression of a Boolean function. Any questions about that? Right? In order for this function to be equivalent, right, all you need to do is cover all of the ones. But and there are 100 ways you can do that, and it'll be fine. But if we want to come up with the simplest possible expression, you want to use the least number of prime or largest possible implicants. In this case, it's 2. So what we get from that is that this particular one is f is a plus b in terms of sum of implicants, right? Or you can, of course, express it exactly as z prime plus x prime y. So we now replace each prime implicant by its expression, and that's what we obtain, right? There, what I just said, and that's the minimal form, right? Not the canonical form, still a standard form because it's still a sum of products, but this is the simplest possible form. We call it the minimal standard form. And now we can crystallize the procedure, the algorithm that we use with the k-maps, right? So step 0, put the ones on the k-map. Step -1, draw the k-map, then put the ones on the k-map. Then find all prime implicants, find all largest implicants that are sufficient to cover all the ones. Then we find all essential implicants. And we'll talk about that in a second. A prime implicant I is essential whenever it contains a one that is only covered by implicant I. Right? So in this case, right, both A and B are essential, right? Can somebody tell me why both of these prime implicants are essential, right? You can have a very large implicant, but may not be essential. But what makes both A and B being quite small, actually, what makes them both essential?
There's another implicant that could cover all the ones.
So yeah, so for example, for A, if we, it's subsumed the blue ones. So for A, like this one, and this one, 3 ones are not covered by any other. It's not covered by B. Yeah, so that makes A essential. On the other hand, for B, this one is not covered by A. This one is, right? So, but this one is not. So it's uniquely covered by B, right? So it makes both of these prime implicants essential. Right? So once we found all the big implicants, now we're determining which one of them are essential, and in this case, both are. And the essential implicants must be in all minimal forms. And that also tells you that potentially you can have more than one minimal form, right? Not in this case, but in some other cases, you may have another form that is, also a sum of products, which is, as simple, right? That will have as few literals as this one, right? So whereas canonical form, made of min terms, is unique, minimal form may not be unique. But in order for it to be minimal, it must contain all of the essential implicants, right? So these, or in other words, all the essential implicants must be in all possible minimal forms, right? In this case, there is just one, right? And this one definitely contains both B and A, right? Because it's A plus B. Any questions about that? Right, so all essential implicants are prime, but not all prime implicants are essential. They are in this case, but there will be other situations where we may have a prime implicant that is not essential. Okay, now the purpose of this whole procedure, of the K-map procedure, is to cover all ones with the least number of prime or largest implicants. And then, of course, once we have done all of this, we are ready to write the minimal form, right? So step 3 is this form, and then step 4 is this minimal form. Again, here I have the procedure again. So this page you could print out and just have it so that when you're doing it, you can just like go through the steps and be done with it. So now we're going to look at a slightly more.
Sorry, can you go back for 1 second?
Yes. Oops, I went too far back. Okay, 1 second. Let's do it this way. How far back are we going?
Just to that one page with all the steps. I was going to take a screenshot.
Okay, that's reasonable. I'm also posting these slides right away. I think I've been pretty good about it. We have time. We have time. Any questions in the meantime, right? Because we're covering new ground every day here. Which is what happens in the summer course. Also, I encourage everybody to ask me questions and answer my questions, because we have a few students who are very good at answering my questions, and I'm sure that the rest of you also know the answers. But it's good to not to be timid to to speak, because you will have to speak up in your life, right? When you get jobs, right, and then you want to make sure that you speak up in the interview so they hire you, and then when you're working there, you want to speak up and eventually get promoted, right? So you have to be your own advocate and in your life, and to be able to do that, you have to learn it, and this is where you practice it, right, in college. So okay, there is the procedure coming up, right? Because the stakes here are low, right? Even if you don't answer the question right, it's fine. You're not going to be punished. Just do it. Yeah.
All right, I got it. Thank you.
Okay, and it disappeared. I'm going to post these slides. Okay, so now let's look at the more complicated K-map or Karnaugh map that has not just X, Y, and Z, but has one more variable. The idea is the same, right? It's just now that we're going to take our, eccentric rectangle and stretch it down to make it more like a square, right? So we have X, Y, and Z areas just as they were before, but now we're going to make another variable t, right? And for t, like for z, the true value is going to be this middle stripe, and the complements are going to be in these little thin stripes above and below. But because it's our torus, our bagel, they will connect in the back, and they will become, the complement of t will become contiguous, right? Any questions about that? No? So in fact, it works like z, only horizontally instead of vertically. Okay, so here's an example of some Boolean function made up of 4 variables that will have ones in these squares, or these are going to be the min terms, just numbered. So you can express a Boolean function like that. How can we immediately tell that this function has 4 inputs or 4 variables?
There are greater than 8 inputs.
That's right. The number, right? Like in this case, we can immediately say, because we see the largest number of min term is 15, right? So yeah, if you're going to have at least 15 squares, and obviously you could have either 1 or 2 or 4 or 8 or 16, right? So in this case, to get 16, you need 4 by 4, right? So you need a 4-digit binary number to get to 15, right? And each digit represents an input variable. Okay, so the answer is correct. And we're going to give all possible minimal forms. I guess there are going to be more than one, right? So we're going to write the decimal numbers, these numbers, in binary, and then as min terms to put them on the K-map. So we're simply going to convert these decimal numbers into binary, right? 0, 5, 4 plus 1, 7, 4 plus 2 plus 1, then 8, then 8 plus 1, 9, then 8 plus 2, 10, then 8 plus 2 plus 1, 11, and then 8 plus 4 plus 1, 13, and then 8 plus 4 plus 2 plus 1, 15. Okay. And now we can simply convert each of them to min terms. So if it's xy, or let's say x, y, z, t, right? So then it'll be x complement, y complement, z complement, t complement, and then on the other hand here it's all true values x, y, z, t. Yeah? So we'll just do that. This is conventional. Let's just do it always that way, even though it sort of doesn't make sense where it's x, y, z is alphabetical, but then t is not. We'll just do it. I mean, it doesn't matter. It will work no matter what, but just easier to read. Well, and also, well, if we start, switching, commuting them, right? Then our sort of truth table arrangement, breaks. So let's just do it this way. Okay. So now, based on these min terms or their binary expressions, or even if you memorize how they get arranged, these numbers, we're going to put ones on the map, right? In any case, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9 ones. Right? 9 min terms, 9 binary codes. So this is square 0, 1 goes there. Square 5, 1 goes there. Square 7, 1 goes there. Square 8, 1 goes there. Square 9, square 10, square 11, square 13, and square 15. If you do it a bunch of times, you'll sort of remember the numbers of the squares, but you don't have to right now. Yeah, you simply, do it using the min terms, right? So for example, I don't know, let's pick square 11. It's this one. It's 7th in the sequence, and it's x complement of y z t. So x complement of y, so it's this area. Then z, this area. Oh, complement of z, sorry. No, z, right. Z is this area, and then t is this one, right? So we got this as the square 11. So we have our 9 ones on the map. Any questions so far? Okay. And now homework, right? The first homework today is to finish this using the procedure and give all minimal forms. If there is just one, you give one. If there is more than one, so you just follow the steps in the procedure, with the prime implicants, then figure out which ones are the essential ones. Okay, so that's the homework. And we'll start doing it together. We'll just mark all of the prime implicants now. So let's do it together. Can somebody just give me, there is a bunch of prime implicants here, so give me one by just naming the red numbers.
13, 15, 7, and 5.
Yeah, that's a nice one. Right, so it's a nice sort of like long implicant, but they're all touching. Okay. Somebody else, another one, another prime implicant.
0, 8, 10.
So the student says 0, 8, 10. Does everybody agree with that? 0 does touch 8, so that's good, but what's bad?
Oh, just the 0 and the 8.
You could do 0 and 8, that's an implicant, but it's not very large, so could we go larger? So let me just parse this. 0, 8, and 10 cannot be. Can somebody tell me why? Even though they are contiguous.
It's both Z and C prime there. And X. And
That is correct, yes, but even faster than that. Right? We should remember that the implicants can be the size of powers of 2, right? So you can have a trivial implicant that is 1, then you can have an implicant that is 2, right? You can have an implicant that is 4, ones, right? Or 8, yeah, or 16 or 32, but you can all have 3 or 5 or 6 or 7 or 10 or 12, right? So 8 and 10 or whatever, 0 and 8 would be like a little implicant, but how about a bigger one, right? We're looking for prime implicants, like the biggest possible. So here 5, this implicant 13, 15, 7, 5, that's, I don't think you could stretch it bigger than that. So are there any other ones?
What about 9, 11, 8, 10?
Yeah, absolutely. We have a nice, square, implicant, has as many ones as the first one. Well,
I guess I'm a little confused because the only thing that's next to the 0 is the 8. So unless we just want the 0 up on its own,
yeah. We'll get there. I just wanted you to immediately give me like big prime implicants, right?
Oh, okay.
And what Anna, I think, just said is this one, 9, 11, 8, 10. And it's a nice prime implicant that doesn't intersect the first one, right? But we're not looking for essential ones yet. We're just looking for primes. And this green one is also a prime, also has 4. So these, each one of them encompass 4 ones.
Professor, before we move on, I have a question.
Yeah.
Could another one potentially be 13, 15, 9, 11, 8, 10? Because like it's still under the X.
It looks nice, but it can't because it's not 8, right? It has to be double, like you has to be a power of 2, right? And yeah. Okay, so that.
Oh, okay, I see. Okay, I got it. Thank you.
Yeah. So yeah, we have 3 big implicants, and as I think it was Patrick said, yeah, the remaining one, right? We need to cover that remaining one, right? And that is going to be the last prime implicant here that you need, right? Because the largest ones, they cover everything but that one. So we're going to use this little black one to cover it, 0 and 8. Yeah, I just wanted you to show me the big ones first. And the follow-up question, could I cover this single one here in another way that is, still going to be, equivalent in a function, but will not be prime?
Yeah, just X complement, Y complement, Z complement, T complement.
Yeah, you can have a trivial implicant that has all 3 inputs, and it would cover it and it will be fine, but it will not be a minimal form, right? Because having this, even though it's small, it's still a prime implicant, right? It has 2, it covers 2 ones, and because of that, instead of being X, Y, Z, it's going to be just just 2 of them, right? So that with what we have here, we'll be able to come up with the minimal form. Now, I here have 1, 2, 3, 4 prime implicants. So let's call them A, B, C, D. Will your minimal form have all 4 of them or no? Or will any of your minimal forms have all 4 of them?
It shouldn't.
It shouldn't. Why?
Because we have implicants that are within other implicants in this.
That's right. That's exactly right. So these 4 prime implicants, yeah, they're all prime, but not all of them are essential. Yeah, and our minimal forms will only have the essential implicants. And the essential ones are the ones that cover ones that are not covered by anything else. Right? So you'll have to figure that out. Right? Okay, that's the homework. And the second homework is to give all minimal forms for a function. And this was going to be, yeah, this function is different. It looks similar, but it actually is different, right? In at least 1 term. Oh, 2 term. Anyway, yeah, it's a different function. So here in 13.1, you use this K-map, and then for 13.2, you'll have to draw a new one. Okay. But then you do the same thing. Here we're going to look at an example with a function that has multiple minimal forms. Okay, so this is the function 0, 2, 3, 4, 5, 7. So three variables because they fit into 8, x, y, and z. Right, so we're drawing the K-map. So that's the square 0, square 2, square 3, square 4, square 5, square 7. Right, they sort of weirdly go. It's like this: 1, 2, 0, 1, 3, 2, 4, 5, 6, 7. But you don't need to know this because you can just quickly convert it into binary numbers and X, Y, Z. Okay. All right. So now let's circle the prime implicants. So we don't have really big ones. So A, B, they overlap, but that's okay. C, D, and one more, E. Right, so all of them are not very big, but yeah, these are the prime implicants: A, B, C, D, E. Each one of them only covers 2 ones. Okay. Oh, sorry, I missed F. One more. That's complete. A through F. Now we're going to pick the essential ones. Right? And a set of essential implicants may not be unique, right? And that's how we get multiple minimal forms, right? So, or in other words, none of them are essential, right? But you will have to pick a set or a subset of them to come up with a minimal form, right? So to say that none of them are truly essential is to say that not a single one is covered by a single implicant. In fact, in this particular silly, or extreme function, every single one is covered by how many implicants? Is it every single one? Not every, most. Yeah, well, 2, exactly. All of them, each one is covered by 2 implicants. Yeah, each one. Okay, so how can we cover all ones with the least number of prime implicants, right? So we need at least implicants in the minimal, we need the least implicants in the minimal form to cover all ones. There are 6 ones, right? So let's try to cover them with 3. Yeah. So in this case, we can cover all of the ones with just 3 prime implicants. But which ones, right? It's a toss-up, right? You can cover it in 2 ways. You can cover it, let's say, with A and C and D. E, I'm sorry, it's E, right? Or you can cover it with D and B and F, right? So these are 2 completely different minimal forms, but they express the same function. So the first minimal form is going to be complement xy plus xz plus complement y complement z. And the second one is yz, x complement of y, and x complement z complement. Right? So these are not mean terms, but these are standard terms, and none of them overlap here. Any questions about this? Pretty straightforward. Okay. So we have the 2 minimal forms here, right? So in your homework, you may have that. So we have a few minutes. Actually, we don't have a few minutes left. I think that one picture from the publisher slide is really all we needed to see. Are there any questions? So we finished at 1:14. So if no questions, I'm going to post these slides, and I hear a question.
Tomorrow, are we gonna have a review for the midterm?
So normally when in the summer session where everything happens so quickly, do you feel that you need a review?
Yeah, it would be pretty useful to have.
Okay, then
Yeah.
let's do a review tomorrow. Okay.
Yeah, if we can talk about
Should we,
sort of
should
what
we
the
take
format is.
should we take a vote? Should we take so I think like 3 people want to review. Everybody who wants to review, raise your hands. All right, so less than half. Should we? Okay, all right. Okay, we'll have review tomorrow. Very good. Okay, no problem. Yeah, you can lower your hands. So we'll have review tomorrow. Sounds good. All
Professor,
right.
could you not forget to, like, could I still submit the homework that was due today?
So that we don't forget it, let's do it right now. Thank you for reminding me. Grade this.
Okay, thank you.
Stop recording, but I'm not signing off. I'm going to stay here until it's done.